In this chapter, we're going to introduce you to the enormously large field of organic chemistry. Organic chemistry is carbon-based chemistry. So these are carbon molecules that are reacting and carbon molecules that are being formed. As we'll revisit on the next page, carbon has a pretty unique bonding pattern. There's lots of different types of structures that can form from carbon-based molecules, meaning there's an infinite amount of different types of molecules that you can create. Organic chemistry is the study of the chemical reactions that are used to produce this wide variety of carbon-based molecules. There's a lot of different categories of carbon-based reactions that are used to produce the wide variety of different types of carbon molecules. If you think about the carbon molecules that you're aware of just from living and experiencing things, the polymers like polyethylene, polypropylene, Teflon, polycarbonate, those are different types of carbon-based molecules that are pretty big. The chemistry that's used to produce those different plastics, those different polymers, they're all different. The medicines that pharmaceutical companies produce, to make those medicines are typically carbon-based medicines, and you need to know organic chemistry to produce those. The nanotechnology that you hear about, those nanoparticles that are being used and applied to different applications, it's carbon-based structures that are forming those nanoparticles or nano instruments that are being produced. You need to know some carbon-based chemistry in order to create those. Organic chemistry in this chapter will give you an introduction to it. A lot of you have to take a full year of organic chemistry next year. This chapter is just to get your feet wet into that particular science. This table should look familiar. It's something that we learned in Chemistry 162. It's something that your organic chemistry teacher would expect you to know going into your organic chemistry class next year when you transfer to a university. This table shows bonding patterns, typical bonding patterns for atoms based upon what period they're in. If you remember, carbon forms 4 bonds. A typical bonding pattern is that carbon doesn't have lone pairs. That's a typical bonding pattern. You're going to see lots of examples where carbon does not follow the typical path. But having 4 bonds, 4 lines, they could all be 4 single bonds. It could be 2 double bonds to 2 different atoms, or maybe a double and 2 singles to 3 different atoms. If you remember, what pattern arises depends upon what atoms are bonded to carbon. There's lots of possibilities for carbon. That's why there's a lot of different types of carbon-based structures. If you remember hydrogen's bonding pattern, it's to follow the duet rule, 1 single bond, no lone pairs. Nitrogen, 3 bonds and 1 lone pair. Oxygen, 2 bonds and 2 lone pairs. Those halogens, 1 bond and 3 lone pairs. Oxygen could have a double bond to 1 atom or 2 single bonds to 2 different atoms. So examples that we gave in Chemistry 162, here's the formula for formaldehyde, and the carbon has 4 bonds, a double bond to oxygen, and 2 single bonds to the hydrogen. All 4 atoms obey the common bonding pattern. Oxygen forms a double bond, so 2 bonds to carbon, and it has 2 lone pairs. If we drew acetic acid, I know we've drawn that structure a lot this year. One of the carbon has 4 bonds around it and it has 4 single bonds. The other carbon has 4 bonds around it, but it's only bonded to 3 atoms, a double bond to oxygen and 2 single bonds. 1 single bond to carbon, the other single bond to an oxygen. The 2 oxygens have different bonding patterns. They both form 2 bonds. This oxygen is bonded to 2 different atoms. This other oxygen is bonded to just 1 carbon atom. So these are neutral molecules and they all obey the common bonding pattern. When you react, if you have a chemical reaction, you may have an atom in the structure that may not obey the common bonding pattern. Acetic acid can do an acid-base reaction and form acetate, and one of the oxygens doesn't obey the common bonding pattern, which is fine. And we've shown this acid-base reaction a lot. This bond breaks, the bonding electrons stay with the oxygen, and you form this anion of acetate. This oxygen obviously doesn't obey the bonding pattern, but it's perfectly stable. There's other carbon-based anions that can form, and you'll learn about this chemistry next year when you take organic chemistry. But let's say you had a neutral carbon-based molecule, it's like methane, so CH4. There's bonds, and any bond can be broken. What if one of these bonds was broken and the lone pair stayed with carbon? So there has to be something that would collide with enough energy to break that bond, and something that could take that hydrogen away, meaning it has a lone pair that that hydrogen could bond to. Just like a normal acid-base chemistry. But if that reaction happens, so that H plus goes with something else, and I'll just write the H plus up there like that, but you're left with this carbon bonded to 3 hydrogens, and it still has those 2 electrons that used to be bonding. This is an anion. If you see a carbon-based molecule and it only has 3 bonds and it has a lone pair, it's probably an anion. You'll definitely see this type of chemistry next year when you take organic chemistry, and I'm assuming that all of you are going to take organic chemistry. Another type of anion that could form is a carbon-based molecule that has a nitrogen atom. You'll learn next year how to name this molecule, but it's called methylamine. But there's carbon bonded to nitrogen. There's 2 covalent bonds on nitrogen and a lone pair. There's 4 single bonds around the carbon. This molecule could react, and there could be a reactant, I'll just draw a circle, that could knock a hydrogen away. And again, it would have to have a lone pair for that hydrogen to bond to. But if we assume that bond breaks and the lone pairs stay with nitrogen, you're going to form an anion. You're knocking a positive proton away. You're losing a positive charge. What's forming is something that's negative. When you start looking more closely at carbon-based molecules in organic chemistry, when you see a nitrogen which is 2 bonds and 2 lone pairs, most likely it's an anion. And it was created from some chemical reaction. So, there's different types of anions. You may see an oxygen with a single bond and 3 lone pairs. That's probably an anion. If you see carbon with 3 bonds and 1 lone pair, that's an anion. Or nitrogen with 2 bonds and 2 lone pairs, that's an anion. Being able to recognize if something's an anion or not is something you'll have to do. All of these, compared to the common bonding pattern, have 1 less bond than what they had in a common bonding structure, meaning some bond was broken and it's left with still the lone pairs are still there. Carbon-based molecules can also form cations, and this same amine molecule that we have down here could go through a reaction and form a nitrogen cation. That sounds familiar. That's because you've done this reaction before. You could have this amine nitrogen compound react with some sort of acid and bond an H plus bond an H atom. So just the generic name of some acid, and it's losing a hydrogen atom, and it makes a bond to the lone pair on that nitrogen. We're going to form an amine cation, and I'm pretty sure you can draw the structure. If you ever see a carbon-based nitrogen molecule in organic chemistry and there's 4 bonds around the nitrogen, it's most likely a cation. Another cation that can form is when a carbon-carbon bond is broken or a carbon-hydrogen bond is broken. You'll learn how this chemistry occurs when you get into a more advanced organic chemistry class, but let's just say we had methane again, and it reacts with something, but whatever that something is, and we'll just kind of draw it as a circle, there's a collision. Instead of the bonding electrons staying with carbon, those bonding electrons and the hydrogen go and make a bond with whatever it's colliding with. So what's left over, and we'll squeeze it in somewhere, is carbon with 3 bonds, but it lost 2 electrons. It lost the bonding electrons. This is carbon. This is a carbon-based molecule. It's a carbon-based molecule that's a cation. It lost 2 electrons and it lost 1 positive proton. The net result is it has a +1 charge. It has 1 more proton than electrons in its structure. And anytime you see a carbon-based structure and you have a carbon atom with just 3 bonds around it, it's a cation. When you get into great depths into the organic chemistry and see the mechanisms, see the pathways, not just the reactants to products, but what's happening in between, you'll see these carbon-based cations and carbon-based anions formed before the final product is formed. And note, being a carbon-based cation, not obeying the octet rule, that's not a very stable structure. It's very, very, very reactive. It's not a final product of something you're going to learn about. It'd be some sort of intermediate. As mentioned earlier, there's a lot of unique carbon-based structures that can be formed. For example, some of the largest molecules that exist in nature are DNA molecules. They're enormously big. Starch molecules, which are about 10 to 20 times to maybe 100 times smaller for some of the bigger starch molecules, could be around 40 million grams per mole. That's a huge molecule. DNA molecules are a lot bigger. Protein molecules, they're amino acids that are bonded together. They're carbon-based structures. These large molecules that can form are called chains, and they can be kind of big, maybe 100 to 1,000 grams per mole to tens of millions of grams per mole. I'm going to draw a structure on this page that's a little bit smaller than a DNA molecule because it'll take some time, but I'm going to draw the structure for pentane. The formula for pentane is C5H12. Pentane has 5 carbon-based molecules all bonded to each other. Each carbon atom is eventually going to have 4 bonds around it. Since the remaining atoms are all hydrogen, they have to be single bonds. So these N carbons need 3 more lines, and each line, each bond, is going to be a hydrogen atom. The interior ones, each one has 2 bonds, so 2 more lines, and this end one over here, 3 more lines. And then we'll put hydrogens all the way around, and if you count it up, there's 12 hydrogens. And again, this is called pentane. You can make a molecule that has that same formula, but it's different, meaning it has 5 carbons and 12 hydrogens. But its bonding structure is a little bit different. It still has carbon bonds, single carbon bonds between them. So maybe I'll write 1, 2, 3, 4. But what's a little different compared to pentane? Pentane, it was 1 carbon atom after another. In this structure, one of the carbons is going to branch off. So this is different. What we're going to come up with is different than pentane. Same formula, but it's a different molecule. If we were going to connect enough hydrogens so that they all obey the octet rule, there's 4 bonds. They have to be single bonds. This N carbon needs 3 more single bonds, which will all be connected to hydrogen. This carbon on the bottom needs 3 more bonds. This carbon on the end also needs 3 more bonds. The one to the left of that needs 2 more bonds. And the last one, this carbon atom right here, it currently has 3 bonds, so it needs 1 more bond. This is a different molecule, and in fact it has a different name. In a little bit, you're actually going to learn how to name this simple carbon-based molecule. It's not pentane. The chemical properties of these 2 molecules would be different. The physical properties would actually be different too. Same bonds, same formulas. Having the same formula, though, doesn't mean that you're the same molecule. And we gave that sort of example during our Chemistry 161 series when we compared ethanol and ether. They both have the same formula, C2H6O. Ethanol has this sort of bonding pattern, And if you remember our example of ether, it's been a little bit, but 2 carbons, 6 hydrogens, 1 oxygen, but the skeleton structure is carbon bonded to oxygen bonded to another carbon. That's different than our structure up above. The chemical properties would be different, and so would the physical properties. We'll see in a little bit chemical properties are related to the type of bond you have. Alcohol has this OH bond. You don't see that sort of bond in here. The chemical reactions would be different for ethanol compared to ether. Other structures that are unique for carbon-based molecules is the fact that they can form ring structures. And we gave an example in class of benzene. Benzene has 6 carbons and 6 hydrogens. All the carbons are connected to each other. So it has this 6 carbon ring structure. Between the carbon atoms, it alternates single, double for the bonding patterns. On each carbon, if you looked at each carbon, there's 3 bonds coming off of it. To obey the octet rule, to have that common bonding pattern, each carbon needs 1 more hydrogen. And the formula for benzene is C6H6. And if you remember, we said this alternating single, double makes for delocalized orbitals, and we'll revisit that in just a little bit. But as far as chemical properties, which you'll learn about a little bit in this chapter, benzene has bonds that are different than any of the bonds in these other molecules on this page. There's no oxygens, there's no double bonds in pentane or ether or alcohol. The chemical properties are different. What type of reactants can react with these various carbon-based chemicals that are on this page are different, which means the chemical properties are different. As mentioned earlier, carbon-based molecules can get enormously big, and taking the time to write out the structures could take quite a few hours. Even something as small as a triglyceride that has 50 some odd carbons and around 100 hydrogens, that could take a long time. There's shorthand notation to greatly simplify the writing of the structures of carbon-based molecules. First, let's look at an expanded type of structural formula. Expanded means that you're showing all the bonds. So here's an example of butane. There's 4 carbons and 10 hydrogens. And I'm just going to label the carbons as 1, 2, 3, 4. How could you draw this in some sort of shorthand notation? And there's actually going to be a number of different ways that we're going to see. But if you look at the carbons that are part of this structure, if you look at carbon number 1, there's 3 hydrogens that are connected to it. And then it's bonded to another carbon atom. Carbon number 2, instead of being bonded to 3 hydrogens, it's only bonded to 2. So I'm going to write it kind of like that. And 2 lines indicating it's being bonded to 2 other carbon atoms. Carbon 2 and carbon 3 have a similar pattern, bonded to 2 hydrogens and bonded to 2 carbons. Carbon number 4 is a mirror image of carbon number 1. It's bonded to 3 hydrogens, and it's bonded to, right there would be to another carbon. What could you do to make it a little simpler? Well, if you look at carbon number 1, there's 3 hydrogens, so maybe writing something like CH3 and a line there. That carbon's bonded to 3 hydrogens. It's simplifying it because you don't, in this format, you're not showing the bonds. Carbon number 2, I'm going to write 2 there. Carbon number 2, it's bonded to 2 hydrogens, so putting an H2 next to it and lines like that. So that carbon, it's bonded to 2 hydrogens. That's what this part is telling you. The 2 lines there, that's telling you that's being connected to something else, and in this case, it's carbon. Carbon number 4, it's also CH3, but if we were orienting it, it would be to the left. So these are the pieces. Let's put them together to simplify this. So when you write it, carbon number 1, it's CH3. There's a bond to carbon number 2, CH2. And then carbon number 3, it has the same pattern. It's CH2. And then carbon number 3 is bonded to carbon number 4, which has 3 hydrogens. This structure is telling you the same thing as the expanded structure. Writing it like this without showing all the bonds is called the condensed structural formula. And you may think this is the only way to draw a condensed structural formula. There's actually quite a few different ways. So in this particular way, you have the 4 carbons, or all the carbons. You're still showing the bonds that are occurring between the carbons. Well, another way to do it is still draw the C's and the H's and write how many there are, but don't put lines between them. It's just assume that you know that there's bonds. We eliminated the bonds between the carbon and hydrogen, so why couldn't we write this butane structure without the bonds between the carbon? So you could write CH3, CH2, CH2, CH3. All of these structural formulas tell you that it's butane, and this is one way of doing it with an expanded structural formula showing all the bonds. Here's a second way, and here's a third way. And there's a fourth way. So what could the fourth way, how could we even simplify it even further? Well, if we look at this structure, CH3, there's a repeating of 2 CH2s. You can group repeating carbons together, and it would look something like this. So we have CH3, there's CH2, but there's 2 of them that repeat in a row, and you can put parentheses around the repeating carbons and write how many are repeating. In this case, it's only 2, and that says the same thing as this structure up here. And we'd have to finish it off with our CH3 on the end. This is another way of saying this is butane. And you may say, well, how does this save you any time? It seems like it may be taking a little bit more time to put it in parentheses. Well, yeah, if there's only 4 carbons there, it really doesn't save you much time. But what if it was 8 to 20 carbons in a row that were all CH2s bonded to each other repeating? It could save you some time when you're dealing with the bigger structures than butane. One note at this point, some of you may be saying, well, can I move this CH3 and repeat it with that? And the answer is no. When you draw structures, structural formulas, you're trying to show what's bonded to what. This carbon in this CH3 is not bonded to that carbon, so you don't put them next to each other. You need to put it next to what's bonded, meaning you should be able to go from this structure back to that structure. So it should make sense. Okay, so these are all structural formulas. In all of them, what we've done is we've basically eliminated the bonds from having to draw the bonds. It would be nice if we actually didn't have to draw the letters, or at least minimize how many letters we have to draw. I'm going to draw a structure that means butane, and it looks something like this. So I make a line like that, down and up again. That's butane. What's shown here are just the bonds between the carbon. At each point, that represents a carbon. So I'm going to draw the same thing over here. This is carbon 1, that's carbon 2, that's carbon 3, and that's carbon 4. Drawing lines like this is a pretty fast way, no matter how big or small the molecule is, compared to writing the symbols, compared to writing all the bonds in there. This one just shows the bonds between the carbon atoms. You need to realize, because you'd have to be able to work backwards from here to there, how would you do that? At each point it represents a carbon, and you need to realize that each carbon needs 4 bonds. So carbon 1, there's a carbon there. How many hydrogens? There's only a single bond coming from it. There would need to be 3 more hydrogens connected to it to give it 4 bonds. Carbon number 2, at that point, it has 2 bonds connected to it. It needs 2 hydrogens. So 2 single bonds to 2 hydrogens. If there's a double bond in a carbon-carbon double bond in the structure, when you write this line formula, you need to indicate that it's a double bond. So what if we had this particular structure? So there's 4 carbons in a row, like in butane, but between carbons 1 and 2, there's a double bond. So we're still going to have that structure where there's 1, 2, 3, 4, but there would be a double bond there, and you'd put a double bond between those 2 carbons. These are the same 2 structures, and it's different than that one that only has single lines. If there's other atoms besides carbon and hydrogen, when you draw these line structures, you don't include the carbon and hydrogen, but if there's another atom, like an oxygen, you would. So what if we had this structure? So we have 4 carbons in a row like butane. If this is 1, 2, 3, 4, on this third carbon, it's also bonded, well, it's now bonded to an oxygen, and it's doubly bonded to an oxygen. So if we're going to draw the structure, there's 1, 2, 3, 4. On that third carbon is an oxygen, and there's a double bond. So putting a double bond and an O there. These are the same 2 structures. So here are 5 different ways of showing structures of molecules. Obviously, the line one is the fastest one, and if you take organic chemistry next year, that's what your instructor is going to do mostly when they present new material. Sometimes the instructor may use a combination of the different types of notations. For example, for butane, we kind of started out with this notation, CH3, CH2. Sometimes they may just throw a line in there too and complete it without bonds between the carbons. You may see a combination of both. You may see a bigger molecule. Part of it has the symbols for the atoms. Part of it may just have the line notation. You'll get used to it as you keep working with the different examples, the different material that they present. For this class and for this exam that you're going to have, you can draw the carbon-based structure however you want. If you want to use some shorthand notation, you can. If you don't want to, if you just want to draw all the bonds, you can do that too. Hydrocarbons are a class of carbon-based molecules that only contain carbon and hydrogen. There's different subclasses of hydrocarbons. One of them is an alkane. If you're a carbon-based molecule and you're considered an alkane, every carbon atom in that structure is bonded to 4 different atoms by single bonds. There are other subclasses of hydrocarbons, and one of them is an alkene. If one of the bonds, one or more of the bonds in that carbon-based structure, if one of the carbon bonds is a double bond, it's considered an alkene. If there's a carbon-carbon triple bond within that carbon-based structure, it's considered an alkyne. And if there's that 6 carbon ring structure with alternating single, double, it's considered an aromatic. We've seen examples of all 4 of these in class. For example, methane, CH4, that's an alkane. Only carbon single bonds connected to it. An alkyne, we did it for ethene, and you saw this structure in Chemistry 162 when we worked on hybrid orbitals. Remember pi and sigma bonds? There's an example of an alkene. There's a carbon-carbon double bond. An alkyne, we also saw that in Chemistry 162 when we discussed hybrid orbitals. But there's an example of an alkyne. And an aromatic, we've already seen, that was benzene on the previous page. So, previous page, there's benzene. What would you say pentane is? So if you look at pentane, there's carbon, 5 carbons, and there's only single bonds. Pentane is an alkane. If you see this structure, which we haven't named yet, which we will name in a little bit, it's also an alkane. Benzene, well, benzene is an aromatic. Ethanol and ether, there's oxygen. They're not hydrocarbons. They have a different type of unique bonding structure. These unique bonding structures, and giving them names, these are called functional groups. Having a carbon-carbon double bond is a unique bonding structure compared to just carbon-carbon single bonds, like in an alkane. Having a triple bond, chemical properties change based upon what types of bonds are in the molecule. Like, for example, ethanol has the OH bond, ether doesn't. And as we mentioned earlier, chemical properties are related to what type of bonds are in the carbon-based structures. There's a lot of different types of bonding structures that could exist in carbon-based molecules. A unique bonding pattern is called a functional group, and we're going to see a lot of different functional groups on the next slide. Shown on this slide and the next two slides are functional groups, and it's a characteristic bonding pattern, a group of atoms that are bonded together with certain types of bonds. And when I say certain types of bonds, like single, double, and triple, the first three we've already seen. So alkene, alkyne, and aromatic. And if you have an alkene functional group in a carbon-based molecule, there's a carbon-carbon double bond. And here's an example, a little bit different than the ethene. This is propene. The next one is alkyne, and if you see a carbon-carbon triple bond, and if you see that in a structure, that's a alkyne functional group. And this one has 3 carbons instead of 2, like our previous example, but it's an alkyne. Now note, when we've given lines like this next to structures before, we've just put X and saying X could be any atom. Well, in organic chemistry, instead of X, they use R. And R could be any atom or a group of atoms. So we'll write that definition. R could be a lot of atoms, meaning this could be a really big molecule, or it could be one atom. If we look at it in our example over here, here R would equal H. Over here, R equals this CH3. It could be a lot bigger than that, but it just means a group of atoms or an atom. An aromatic, so this is like benzene, and here's our benzene example. Remember, that's called an expanded structural formula. You could use some sort of condensed structure. If I was going to draw it with just lines, so no C atoms, no H atoms, how would it look? Well, we'll draw our hexagon. So at each point, there's a carbon atom. There's 6 atoms, and it alternates double, single, double, single, double bonds. So that represents benzene too. Because that alternating single, double forms a big delocalized orbital that spans all 6 atoms, for benzene and for aromatic structures, you can still draw this line formula. Instead of drawing the alternating double bonds, a circle means that it forms one big delocalized orbital. This is often, in organic chemistry, how an aromatic 6-ring structure is represented. A lot of functional groups in carbon-based molecules contain an oxygen atom. So why would an oxygen atom be classified as a functional group? What do we know about oxygen? Oxygen is our second biggest sun in our universe of atoms. Has a high electronegativity. It pulls those bonding electrons pretty close to it. It makes for weak bonds. Chemical reactions happen where there's a weak point, where there's a weak bond. Often, carbon-based molecules, when you see chemical reactions, the functional groups, they have high electronegative atoms that are part of that unique bonding structure. You'll see on the next couple slides after this one, we'll see functional groups. Look for oxygen, that's part of a functional group. Look for nitrogen, that's the 3rd biggest sun in our universe, that's part of a functional group. This OH bond is relatively weak compared to a CH bond or a CC bond if you had an alkane. It's a lot easier to break this OH bond than a CH bond up here. It requires a lot more energy to break a carbon-carbon single bond than an OH bond. If you see this characteristic structure, a carbon connected to an oxygen connected to a hydrogen, so this structure here, that's considered an alcohol. And here's our example that we've seen, that's ethanol. You also see that same sort of structure in methanol, so that's considered an alcohol. Or another alcohol that we've shown before is propanol. 3 carbons. We've seen this structure in our 160 series. And each carbon is bonded to, has single bonds connected to all of them. These are considered alcohols. And one note I'm sure some of you are asking, well, is this part an alcohol and this part an alkane? You only have an alkane if it's just carbon and hydrogen and only single bonds. This propanol, methanol, ethanol are considered alcohols. And chemical properties for these 3 molecules are different because of that oxygen, because of that OH bond that's present and isn't present in an hydrocarbon. And another thing you'll note, an alkane versus an alkene versus an alkyne versus an aromatic. Alkenes have a different different chemical properties than alkanes. Having a double bond, there's certain things that can react with a carbon-carbon double bond, and those chemicals don't react with carbon-carbon single bonds. Alkynes, which have a triple bond, that's where the chemistry occurs, at the triple bond, at the double bond. That's why we classify them as functional groups. Aromatic structures have different chemical properties than straight chain alkenes, alkynes, or alkanes. Ether, we've seen this in our example. Instead of 4 carbons in our previous slide, there was 2 carbons. But what makes it an ether? It's carbon bonded to oxygen, then singly bonded to another carbon. That's a characteristic ether structure. That's different than the alcohol, which is carbon, oxygen, hydrogen. This doesn't have the OH bond. This oxygen is bonded to carbon and hydrogen in an alcohol. In an ether, it's singly bonded to 2 carbon atoms. That's a different chemical property. We don't have the OH bond in ether. If we went back to this slide, this is an alcohol, and this bottom one is called an ether. You'll learn how to name that ether. It's called methyl ether. On this example, that's diethyl ether. But you'll learn how to do that as we go through this chapter. On this page is a list of functional groups. All of them contain oxygen. What's a little different on this page is that the oxygen is doubly bonded to a carbon atom. So we see it in that functional group, that one, and that one. What makes each one of these functional groups different from each other is what's bonded to that carbon atom. For all of them, it's a little different. The bottom one is the easiest to see. What's bonded to that carbon atom is a nitrogen. So having a carbon doubly bonded to an oxygen, singly bonded to a nitrogen, makes a functional group that's considered an amide. And we can see that characteristic bonding structure in this particular molecule. Note that this particular molecule has more than one functional group, and in a little bit I'm going to have you label each functional group, but let's learn about the other ones first. But as far as where's that amide functional group, if we look for that characteristic bonding pattern, here's that special carbon. Look, when you're looking for functional groups, look for oxygens, look for nitrogens, and look for the carbon that's connected to those atoms. And we can put a little circle around those. These lines that are coming off the atoms over here, that can be any other atom. So it could be carbons, could be hydrogens. On this nitrogen right there, one of the R groups, that's a hydrogen. The other R group is this whole part right here, and it's connected to that carbon. For the R group that's coming off of this carbon right here, That's this whole portion. R can be anything. Something that's considered an ester, so an ester has that carbon-oxygen double bond in its structure. What's bonded to that carbon is also an oxygen, and it's a single bond. Some of you at this point may be saying, well, a carboxylic acid that's right above it, if you look at that carbon, it also is doubly bonded to an oxygen and singly bonded to an oxygen. So what's the difference? What makes the two different is what's connected to that oxygen. For an ester, what's bonded to that oxygen is another carbon. For a carboxylic acid, what's bonded to that singly bonded oxygen is an H. These are two different functional groups with different chemical properties. We've given carboxylic acid functional groups a lot. Anytime we've presented acetic acid, we've presented a carboxylic acid functional group. A carboxylic acid, it's an acid functional group. That OH bond is a relatively weak bond. In an ester, you don't have an OH bond. You have oxygen-carbon bonds that are single and an oxygen-carbon bond that's a double. So sometimes you have to look at more than just 3 atoms. In amide, 3 atoms was enough. For esters and carboxylic acids, you have to look at 4 different atoms. What's connected to the carbon that's doubly bonded to oxygen can be an H or it could be another carbon. So that's R. If we went over to our different examples for the ester, and by the way, this ester molecule over here is considered a wax. If you went and looked at the 4 characteristic atoms, so it's these 4 that tell you that it's an ester, well, here we go. It's right here. Those 4 atoms tell you that this is an ester functional group. For the carboxylic acid, these are the 4 that tell you it's a carboxylic acid. If you look over here, that's these 4 atoms. That's a carboxylic acid. The top 2 functional groups only contain 1 oxygen. For one of them, it's considered an aldehyde. For the other, it's considered a ketone. And again, finding the functional group, look for the carbon that's bonded to an oxygen or a nitrogen. And right there, it's this carbon we need to look at. What makes it a ketone is what's bonded to this carbon. Because if you have an aldehyde, both of them, that carbon is doubly bonded to an oxygen. What makes them different is what's bonded to that carbon that's doubly bonded to an oxygen. What makes it a ketone is if that carbon is bonded to 2 other carbons. That's a ketone. What makes it an aldehyde is if this carbon is bonded to at least 1 hydrogen. On this other side, it's an R group, which could be another hydrogen or it could be a carbon. But this carbon right here, having a single bond to a hydrogen, makes it an aldehyde. So when you go looking for an aldehyde, you need to look at these 3 characteristic atoms. For a ketone, you need to look at those 4. Over here, here's our functional group that go over that carbon too. That's a ketone. And the fact that it looks like that, it's considered an aldehyde. You've seen both of these molecules presented in our 160 series. This is acetone, and the next one is called formaldehyde. So we've seen both of those. This carboxylic acid is something you'll also learn about in biochemistry. It's considered a fatty acid. This bottom molecule, which is considered a dipeptide, and we have to spell it right, but it's something that's formed from amino acids. It's formed from 2 amino acids. There's 2 more functional groups in there. One of them we don't know the name yet. The other one we do. And the other one is on this page. Why don't you circle the atoms and label what that functional group is? The next one we'll learn on the next page. Pause the video, unpause the video when you're ready to check your answer. Here's a carbon bonded to some oxygens. It's bonded to 2 oxygens. This oxygen is bonded to a hydrogen. It makes it a carboxylic acid. This particular dipeptide would have acidic properties just like a carboxylic acid, just like acetic acid. On the next page, we're going to learn about this nitrogen-containing functional group. The carbon that's bonded to nitrogen tells you what functional group it is. On this page are functional groups, carbon-based functional groups that are cations and anions, and a couple that contain sulfur. The first one we're going to look at is an amine. And an amine, if you look at it, it's carbon bonded to nitrogen. Pretty simple. What's bonded to nitrogen could be an H or it could be some carbon atoms. What's bonded to the carbon that's bonded to nitrogen is carbon or hydrogen. Shown over here on the right is the same dipeptide that we had on the previous page. So we have an amide group and a carboxylic acid group. Here is the characteristic, and it's just two atoms, that tells you it's an amine. So what's connected to nitrogen are two hydrogens. What's connected to this carbon is two hydrogens and a carbon. That makes it an amine group. We've seen lots of amine groups, especially when we did our acid-base chapters previously. Remember those amines, those are the bases that we saw. There's a lone pair on that nitrogen, although it's not shown here. Remember, you don't have to show lone pairs, you just have to realize that they're there. There's a lone pair on that nitrogen that can bond a hydrogen atom, and it can be a base. Another note that we didn't really mention as we went through it, so here's the same dipeptide. Again, this is an amide group, and over here is our carboxylic acid group. And some of you may be saying, well, the amide group, couldn't the amide group be a combination of, say, a ketone and an amine? And the answer is no. It's its own special group. When you look at this carbon that's bonded to, say, an oxygen or a nitrogen, if it's bonded to both, you use those two atoms to define the functional group. You can't split up an amide group into two separate individual groups. If you have a carbon that's part of a functional group, it's only part of one functional group. And having two big suns next to it gives it certain chemical properties than if, say, that nitrogen was a carbon. The same thing for the carboxylic acid. Some of you may be saying, well, can't we just call that a ketone and that an alcohol? And no. Ketones and alcohols have their own unique chemical properties. Having a carbon with both of those oxygens connected to it has different chemical properties than a ketone or an alcohol. The carboxylic acid, having these, how we've explained it before in our 160 series, having two suns next to that hydrogen makes this bond here really, really weak, makes it an acid. The point is, when you're recognizing functional groups, if you have a carbon and it's bonded to two oxygens or bonded to an oxygen and a nitrogen, you can only make that carbon into one functional group, not two. Okay, the next functional group we've seen before, and when that amine acts as a base and gets a hydrogen connected to it, it forms an amine cation. And when you go looking for an amine cation, it's these two atoms, the carbon and the nitrogen. What makes the amine cation different than an amine is that nitrogen is bonded to 4 different atoms, and it's a cation. So if we go looking for an amine cation, there you go in this particular structure. So this is a dipeptide, and the nitrogen reacted as a base and had a hydrogen attached to it. A carboxylic acid anion, this is our acetic acid forming acetate. So here's the characteristic bonding structure. A carbon doubly bonded to an oxygen, singly bonded to an oxygen, and to this oxygen there's nothing. Just lone pairs. Just 3 lone pairs. And here we go. There's our carboxylic acid anion. The last 2 functional groups that I'm going to introduce are thiols and disulfide. Both of them contain sulfur. A disulfide compared to a thiol, there's a big difference. In a disulfide, it's 2 sulfur atoms bonded together. In a thiol, it's carbon bonded to sulfur, and that sulfur is bonded to a hydrogen. So if we look at this particular molecule, that's actually an amino acid. We've drawn amino acids before, and you'll see that in biochemistry. There's a carboxylic acid there. There's our amine group there. Where's our thiol group? Our thiol group, it's right there. The disulfide, this is structured down here, is actually two amino acids connected together. There's a lot of different functional groups. Where's our disulfide? It's where two sulfur atoms are connected to each other. So there's our disulfide functional group. If you look in this structure, there's other functional groups. You should be able to tell yourself what other functional groups are on that structure. There's two of them. And if you keep thinking and thinking, here's an amine cation. That's a shorthand notation of showing an amine cation. So instead of showing the bonds connected to the nitrogen, those three single bonds, it's in abbreviated form. But that's an amine cation. And that amine cation looks just like that if you drew the expanded structure. The other one is the carboxylic acid anion, and it's given twice, and the amine cation is given twice. Note, there's a lot more functional groups than this, but the functional groups shown on these 3 pages are ones that I expect you to know for the exam, which probably means flashcards or just practice the problems that I'm giving you. There's a lot of information in this chapter. There's a lot of information in the textbook that we're not covering. Use the practice problems, as always, to give you a guide as to the type of problems that will be on the exam. One last note, these last 4 functional groups, these last 4 will not be on your exam, meaning you don't have to recognize them. If I gave you a molecule, you don't have to name the functional group. Or if I told you to, and you'll see it in some practice problems, here's the formula, make a structure with this functional group. And you'll see those practice problems in a laboratory. But these last 4 will not be on the exam. So we'll put a circle around that. When a lot of carbon atoms are bonded together, if you remember what we called that, we called them chain structures. And when you have a chain structure, a lot of carbon atoms bonded together, the chain could be considered normal, or it could be considered to have a branch. So what does it mean to have a normal one? So our pentane example, that's a normal chain structure. There's no branching. When you have branching carbons, and sometimes they're a little hard to recognize, but when you have branching carbons, there would be a carbon atom in that chain of carbon atoms that's bonded to 3 or more carbon atoms. And let's give an example of that same molecule that we're eventually going to name that's on the same page as pentane. So 5 carbons, but one of the 5 carbons is bonded to 3 or more carbon atoms. So that could be that carbon. This carbon here is bonded to 3 carbon atoms. There, there, and there. Note, if we wanted to show a branch point, we could have connected the carbon to that carbon. But you wouldn't connect it to one of the end carbons. If you connected it there, you're just making that length of the carbon chain just a little bit longer. This carbon still only bonded to 2 other carbons. Branch is kind of like a tree branch. If you have a limb, if the limb just keeps growing longer, but maybe it starts pointing down, there's no branch point. But if you have a major limb and another limb coming off of that, so say we had a branch and on a tree, so this is my tree, and there's a limb that started growing off of there, that's a branch point. If it just became longer and started pointing down, that's not a branch point. But let's finish and give an example of a carbon chain with a branch. So we'll just put the carbon there, and then it's carbon and hydrogen, so we're going to put enough hydrogens so that there's 4 bonds around it, and all the bonds, all the hydrogens they're always single bonds to the carbon atoms. So here's our definition of a branch carbon. A carbon bonded to 3 or more carbon atoms. Both of these examples, it's C5H12, but they're different chemicals, different shapes, different physical properties, and slightly different chemical properties. We can draw a different molecule with the same formula that has a different branching pattern. So still 5 carbons, but it's going to look a little bit different than this one that we just drew. So what I'm going to do, we're going to draw one that has 3 carbons in a row. So I'm kind of starting with the skeleton structure of the carbon atoms to the middle carbon. If you're going to create a branch, again, you can never start creating a branch from the end carbons. Just because you point it up or point it down, that's not a branch point. But the carbon that you can start making a branch point on is bonded to 2 or more carbon atoms. And just like the one up above, we can put a carbon there. You can put a second carbon there. So there's a branch coming one way there and going that way there. Those are 2 different branches. If you look at this particular chemical, the longest carbon chain, no matter which carbon you start out with, 1, 2, 3. You could also, I'm going to erase that, what's the maximum amount of carbons that are going in a row? It could go 1, 2, 3. No matter which carbon you go on, how many carbons in a row that are bonded to each other is 3. This example up here, 1, 2, 3, 4, you could have started from this carbon as your starting point, and it can go 1, 2, if we went to the left that would be 3, but if we kept going that way, 1, 2, 3, 4. We'll see in a little bit the name of the carbon-based molecule is based upon the longest chain of carbon atoms. You don't have to start from left to right. You can go top, bottom, left, right, whatever direction you want. But what's the longest continuous chain of carbon-carbon atoms? There can't be an interruption with an oxygen. Carbon atoms all bonded to each other. This top one, it's 1, 2, 3, 4, 5. The longest chain is 5 carbon atoms. And lastly, let's finish this structure right here by putting the appropriate amount of hydrogens on each carbon atom. Each carbon, except for the middle one, needs 3 more single bonds. So 3 hydrogens connected to each of those 4 atoms. 3 times 4 is 12. So all the chemicals on this page are C5H12. Different bonding structures, though. So I drew my H's really small. You may have a hard time reading it. But each carbon atom has 3 hydrogens singly bonded to it, and each one it has a single bond to the center carbon atom. All of these structures are alkanes. They're hydrocarbons, but they're alkanes. Although there is a tremendous amount of different types of carbon-based molecules that can be formed, the nomenclature, the names given to these carbon-based molecules, the system is relatively simple. It's something that you're going to have to learn more thoroughly in organic chemistry. For this chapter, we're just going to focus in on alkane nomenclature. So on the exam, I only expect you to be able to name an alkane molecule, like the pentane molecule we saw earlier. This nomenclature was devised by the International Union of Pure and Applied Chemistry, or the acronym IUPAC. The alkanes that we're going to name, they all have a chain. They're not going to be ring structures. And the basis for the name depends upon the longest chain. So when you have this IUPAC name, there's a prefix, there's a root, and then there's an ending. The ending is in reference to the functional group. Since we're only going to look at alkane molecules, the ending for all the chemicals that we name in this chapter, they're all going to end with ane, like alkane. If you had an alcohol, like methanol, ethanol, propanol, what are they all ending in? OL. Alcohols that you'll learn about later when you take organic chemistry next year, their ending is "all." If it was an alkene, their endings all end with "ene." But for this chapter, let's just focus on alkanes. And on the next page, we're going to look at how do we give a name for the root. And again, it's based upon the longest chain of carbons in a row. Shown here is a table of root names that, again, depends upon the longest chain. The longest chain we'll have, as an example, would be, possibly could be 10. And again, there's a lot of carbon-based molecules where the chain lengths are a lot greater than 10. But if the longest chain length was 4 carbons in a row, then the root part of the name would be bute. That's this portion. The ending, since we're only looking at alkanes, would be ane. Butane. Butane would look like this. There's 4 carbons in a row. That's the longest chain. There's no branching. Butane. If we had 8 carbons in a row, and I'm going to make it hard on you, well, maybe easy. I'm going to draw it as a line structure. So 1, 2, 3, 4, 5, 6, 7, 8 carbons. What's the name of that structure? Well, if it's 8 carbons in a row, starting with 1 all the way over here to 8, 8 is oct. And the ending is ane, so this is octane. So there you go. Right now we know the ending, it's always ane for our examples. The root, we can use this table. The prefix, we use the prefix if there's branching. On the next page we'll see how those prefixes are named. Prefixes are used to state where the branch occurs off the longest carbon chain and what is the composition of the branch carbon chains that are coming off the longest carbon chain. So a branch point, remember, for a carbon, if you have the longest carbon chain, it's bonded to 3 or more carbons. The carbon that's part of the branch is not part of the carbon chain. There could just be 1 carbon coming off the longest carbon chain. If that's the case, it could be a CH3 bonded to a carbon that's part of the chain. It's called a methyl group. So how did we get the word methyl? Well, it comes from the fact that if you had a molecule like that, that's methane. To name it as a branch and to put it as a prefix, it starts with meth, but YL is added, so methyl. If it's 2 carbons that are coming off the longest chain, 2 carbons, if it's just carbons by themselves, it's ethane. It's called ethyl. If there's 3 carbons, it's called propyl. And the propyl structure, it could be an N carbon, like what's shown here, attached to the chain, or it could be the middle carbon attached to the chain. If it's an N carbon, it's called propyl. If it's the middle one, it's called isopropyl. So what I just wrote here, these alkyl groups, and just accept that they're called alkyl groups, they're attached to a carbon that's part of the chain. So again, that bond right here, that's attaching to a carbon that's part of the chain. There's groups that could be bonded to the carbon chain that are not carbon-based. You could have fluorine atoms, chlorine atoms, you could have NH2. They have different names. And if you saw any of these groups that's part of your carbon-based structure and they were connected to the largest chain, those names that are listed there in the table would go under the prefix section. But for this exam, for this test, for this class, the only prefixes I want you to know are these 4. So if you saw 1 carbon coming off of the longest carbon chain, that prefix name would be methyl. If you saw 2 carbons coming off of the longest carbon chain, then ethyl. If there was 3 carbons, well, again, it depends upon which carbon is bonding to the longest carbon chain. Is it an end one or the middle one? And your choice would be either propyl or isopropyl. On the next few pages, we're going to learn the steps for naming a carbon-based molecule, and again, just for alkanes. When we do this, we have to indicate which carbon in the carbon chain these groups, these alkyl groups, are bonded to. So we'll see that as part of our system of naming these compounds. Also, there can be multiple groups along the carbon chain. So we may have a methyl, an ethyl, and a propyl. We'll see. There's lots of different scenarios that could happen. On these next few slides, you're going to learn the steps that you need to follow in order to name these carbon-based molecules. And again, we're only doing alkanes. There's two different problems. We're going to do this one first, and then we'll come and name this compound in just a little bit. Step 1 is to identify the longest chain. So this particular molecule, we see that there's 6 carbon atoms, and what's the longest chain? We can start counting this way. 1, 2, 3, 4, 5. 5 carbons in a row is the longest if we started from that endpoint. If we started from this direction, so 1, 2, 3, 4, 5, it's still 5, but the longest chain doesn't have to go left to right. You can curve around. So what if we started at a different place? What if we started with this carbon? It's perfectly acceptable. So 1, 2, 3, 4, 5. It's still 5. So it really doesn't matter, which N carbon you start out with. The longest chain is 5. The next step is we're going to number our carbon atoms that are part of the chain. When you do this numbering, there's a carbon number 1, but which carbon is going to be carbon, that could be 1, this one could be 1, that one could be 1. When you assign numbers, you want to make sure that the groups, the branch points, that group, it would be assigned to a carbon, it's attached to a carbon that's as low as possible. So let's give a couple scenarios on numbering these carbons. Let's say this is carbon 1, so 1, 2, 3, 4, 5. Let's say we decided to start with 1 over here. 1, 2, 3, 4, 5. This CH3, this is a group. Its name is going to be part of the prefix, and it's a group down here. It's actually a methyl group, and we'll name that in a little bit. But down here, it's on carbon number 4. Up here, it's on carbon number 2. This rule is that you number them so that the group is connected to a carbon that's the lowest that you can possibly get. So the fact that here the group is on carbon number 2, you're going to number it that way versus down here when the group is part of carbon number 4. So we'll put a big X on that one. We're doing this one. The next bold is applicable to this chemical, so we'll talk about that in a little bit. The next step is to name the groups. When you name it, you also have to give the number for the carbon atom that it's attached to, the carbon that's on that chain. Let's label them again. So 1, 2, 3, 4, 5. This is the group. It has a name. If we went back to our prefix table, it's the methyl group. So this prefix name is going to have methyl. And it's on carbon number 2 on the chain. So the name of that group would be 2-methyl. If you want to put a dash, you can. I don't care if you do, but 2-methyl. This is the prefix. Next, we're going to combine everything and make the name. So the prefix, it's 2-methyl. Okay, the longest chain we learned about earlier, it's 1, 2, 3, 4, 5. And if we went back to our root section, if the longest chain is 5 carbons in a row, then the root part of the name would be pent. And since this is an alkane, its ending is always ane. The name of this chemical is 2-methyl pentane. 5 carbons is the longest chain. It's an alkane, so pentane. And there's a branch carbon, and that's a methyl, and it's on carbon number 2 that's part of the longest chain. So 2-methyl pentane. Okay, let's look at our other example. It's a little more complicated, not much. It's still an alkane, so it's going to end in ane, but what's the longest chain? If we started here over on this carbon, and we started counting from left to right, so 1, 2, 3, 4, 5, 6, 7. So 7, what if we started from, some other N carbon? What if we started with this carbon? So let's start counting. 1, 2, 3, 4, 5, 6. So 6 is less than 7. So that's not the longest chain. What if we started with that one again, but instead of going right, we went left? So 1, 2, 3, 4, 5, 6. So it's still 6. So far it's 7, but let me just try at least one more scenario. Maybe this carbon. Let's start counting. So 1, 2, 3, 4, 5, 6. 6 is definitely shorter than 7, so 7 is the longest chain. So there we go. Now the next question is number 1 down here, or is number 1 down here? Let's examine that on the next page. On this one, let's say we start 1 down on the left-hand side. So 1, 2, 3, 4, 5, 6, 7. And on this example down here, let's start 1, 2, 3, 4, 5, 6, 7. Okay, there's a few groups. There's 3 groups coming off of this longest chain. This is a group, that's a 2-carbon group, and this is another single carbon group. As far as the carbons, the top one has groups on carbon number 3, 4, and 6. On the one that's bound below, there's a group coming off of a 2, 4, and 5. Which one should we choose? And that's what this bold is telling you. If there's 2 or more groups, and we have 3, use the sequence of numbers that gives you the lowest series of numbers. And that would be this one. 2, 4, and 5 added together is less than 3, 4, and 6. So not that one, yes to this one. We're going to number our carbon chain starting from right and moving over in that direction. So as far as our prefixes, the groups that are coming off of the longest carbon chain, we have a 2-methyl right there. We have a 4-ethyl, because there's 2 carbons on that branch. And we have a second methyl, and it's on carbon number 5, so 5-methyl. Somehow when we piece all these together, these prefixes should be part of the name for this compound. So on the next page, let's put those pieces together. The ending is still ane, and there's 1, 2, 3, 4, 5, 6, 7 carbons in the longest chain. So let's go back to our page that gives the root names. If there's 7 carbons in the longest chain, it's hept. So we have hept and ane, heptane. And lastly, the prefixes. So the prefix has to include the 2 methyl groups and the ethyl groups, and they have to state what carbons they're coming off of. We have 2 methyl groups, so when you do that, instead of writing 2-methyl and 5-methyl, we use di, so dimethyl, which means we have a prefix for the prefix. Okay, so it will be dimethyl. And there's only one ethyl, so we don't need to worry about a prefix for the prefix for the ethyl. You still need to include the number positions, and we would separate them by a comma. So instead of writing 25, it would be 2, 5. And lastly, if you have two different types of groups, which we do, we have methyl and ethyl, you put them in alphabetical order. Ethyl, E, comes before M in methyl. And don't worry about the di, that's not included when you have this particular rule. There's lots of little rules. So, we're going to do the 4-ethyl before the dimethyl. So the name of this compound is 4-ethyl 2,5-dimethyl heptane. Before we move on to another topic, let's go back a few slides, and I want you to name that compound and this compound. Go ahead and pause the video, give it a try. Unpause the video when you're ready to check your answer. For the first one, the longest chain is 4 carbons in a row, and we have 1, 2, 3, 4. You could have started with the 1 there, but no matter where you start with an N carbon, it's only 4 carbons in a row. So we get butane. Off of carbon number 2 is a methyl group, so 2-methyl-butane, and we need to add our L there. 2-methyl-butane. For this other structure, there's at most 3 carbons in a row, no matter where you start with a 1, so it's propane. Off of carbon number 2 are 2 methyl groups, so dimethyl, 2, 2, dimethyl propane. Chemicals have kinetic energy, and this movement can be in 3 dimensions, or it could be the movement within the chemical itself. Carbon-based molecules are in constant motion. That motion can also be the movement within the molecule, the vibration of bonds, the movement of nuclei. There's a lot of energy of movement within the molecule, not just in 3 dimensions, but within the molecule itself. Here's a model of, you should be able to recognize it, that's butane. The bonds in there, the nuclei, the atoms, there can be vibration in that direction. There can be movement in different directions. There's lots of movement within a molecule, and they can take on different shapes. These shapes are called conformations. Over here is another shape that butane molecule could take. There's usually one shape that's the lowest in energy, and on average it's going to have that shape, but that butane molecule, the bonds, and there can be movement, and you can take on different conformations. That's a 3-dimensional structure of a molecule. When you write the structural formula of a molecule, you don't always try and show the exact conformation or any geometry of the molecules. So for example, I could draw butane looking like this, CH3, CH2, CH2. That shows no 3-dimensional structure whatsoever. You could, if you wanted to, write butane a little differently. You could go CH3 and go down CH2 and then across CH2, and maybe you wanted to go down again. You can write these structural formulas however you want. You're not trying to show 3-dimensional geometry. But if you did, you should remember how to draw 3-dimensional geometries on a 2-dimensional piece of paper. We learned this in Chemistry 162 using this table in your information packet. I'm sure you can't use your information packet next year when you take organic chemistry, but you should remember how to draw 3-dimensional structures of carbon-based molecules. You don't need to worry about more than 4 electron groups. Carbon-based molecules, that's all they have. They make 4 bonds. So you may have a tetrahedral structure for a carbon atom, or maybe a bent structure. Remember, there's electron groups, and an electron group is a single bond, a double bond, a triple bond, and a lone pair. If you had 4 groups around it, depending upon how many of those groups are lone pairs, you get the 3 different structures. That's something you should remember if you're going on to organic chemistry next year. For this class and for this exam, all I want you to know is if I drew some carbon-based structure like this for butane, well, that means exactly the same thing. They're not different molecules. They're just different representations of the same molecule on the same piece of paper. I'm not going to make you do this on the exam, but if I wanted to draw the three-dimensional shape of this butane molecule for this particular conformation, the geometry around each carbon atom is tetrahedral. And remember, for tetrahedral, there's two solid lines, a dashed line, and kind of a solid arrow. So there's a tetrahedral structure, a representation using a two-dimensional piece of paper for one of the carbon atoms. This carbon atom, if we call this carbon 1 that's shown, well, here's carbon 2. So this is 2, this is 1 and 2. Here's 3. 3 is going up, so we could put carbon 3 there. And carbon 4, well, that one's coming down, so we could do it right there. So there's kind of the zigzag structure of that carbon skeleton. And on each carbon, there's a tetrahedral geometry. So all of these carbons have solid lines, and the two inner ones have two solid lines. Eventually, on a tetrahedral structure, you need two solid lines, so this in one needs another solid line. A dashed line and a solid arrow also needs to go on each one of those carbon atoms. So maybe our final structure looks something like this. So the solid lines represent a bond, so do the arrows that are in there and the dashed lines. All of them are single bonds, and we have this down, up structure of the carbons. Another concept in carbon-based chemistry is isomers. And isomers, these are chemicals that have exactly the same formula, but they're different molecules. And I've given you examples throughout this chemistry series. I've given the formula of glucose, C6H12O6. Well, fructose has that exact same formula, but their structures, the bonding patterns, are slightly different. So how do you recognize if you have an isomer? So again, they have the exact same formula. They can have the same formula, but different functional groups. Remember, ethanol and ether, the two examples we've shown lots of times this year, they have the exact same formula, but they have different functional groups. When you have this type of scenario, it's pretty easy to recognize. And here's an example. Here we have two different molecules. They have the exact same formula, 3 carbons, 6 hydrogens, and 1 oxygen. However, the functional groups are different. This one is a ketone functional group, and this one is an aldehyde functional group. They're different molecules with different chemical properties, but they're considered isomers because they have the same molecular formula. Another example is they have the same functional groups, but different types of branching. So same functional groups, but different types of branching. And here's an example. Here's a formula for an alkane, C4H10. And one of them, it has the longest chain is 4 carbons. So here's 4 carbons in a row. There's actually no branching. But what if we drew another structure and there was a branch point, and the longest chain was 3 carbons in a row? They're different molecules. This is butane, and it would have certain chemical properties, certain physical properties. This is 2-methylpropane. Different chemical properties, pretty close. They're both alkanes, but definitely different physical properties. The melting point and the boiling point of 2-methylpropane would be different than butane. They're different molecules, same formula, different types of branching. Another one, the third one, functional groups are on different carbons that are part of the chain. And here are 2 examples for alcohol functional groups. They both have 3 carbons, they both have 1 oxygen, and they both have 8 hydrogens. But for the first one, the alcohol group is on an N carbon. For the second one, the alcohol is connected to a carbon that's an interior carbon. The first one, and you'll learn names about alcohol groups when you take organic chemistry next year. The first one, that's propanol. The second one is isopropanol. They're definitely different molecules, and they actually have different chemical properties. This alcohol group being on an interior carbon, it has slightly different chemical properties than an alcohol group that's on an end carbon. And one last note using this slide that we've been to a few times. All the structures on this page are isomers. All of them have 5 carbons and 12 hydrogens. Here's a page with a couple practice problems. Go ahead and pause the video, answer the 2 questions. Unpause the video when you're ready to check your answer. For the first one, it's the same molecule. They both have 5 carbons in a row for the longest chain. It doesn't matter which N carbon you start with, it's 5. Both of them are pentane. This one's just written a little differently on the piece of paper. But when you write it just on a piece of paper to try and represent a structural formula, you can zigzag. It doesn't matter what's top, left, bottom, right. They're both the same molecule. The one below, they're different molecules. If we started counting for the longest chain, 1, 2, 3, 4, 5, that's a pentane for the longest chain. This one, if we started counting 1, 2, 3, 4, 5, they both have the same longest chain, but the place where the methyl group is attached, the carbon that it's attached to, it's a different carbon. For one of them, it's the very middle one, carbon number 3. For the other, it's carbon number 2. They both have the same formula. That's what makes them possibly isomers. So they're C6H14, but they have different locations of their attached group, so they're isomers. So I wrote isomers, the methyl group, I need to get my L on there again. The methyl group is attached to a different carbon on the chain. In Chemistry 162, we learned about delocalized bonding, and we learned to recognize if we saw a certain structure that there's probably delocalized bonding that could occur. Remember, one particular structure was alternating carbon double, carbon single bonds. Another structure was oxygen-carbon-oxygen bonds. And we see that alternating bonding pattern in something like acetate. Carbon-oxygen double bond, carbon-oxygen single bond. This one has 3 lone pairs, well, this being that oxygen atom. The oxygen atom with a double bond connected to it has 2 lone pairs. You could draw a Lewis-Dot structure with this carbon having a single bond and 3 lone pairs. And the way to think about it is a lone pair on that oxygen moves and becomes a bonding pair, which makes one of these bonding electron pairs become a lone pair on that one. And if we drew that, that structure to the right, we could draw a Lewis structure that also seems to work. But remember what we said, delocalized bonding, these Lewis-Dot structures, they're not real. All it really means is there's a bonding orbital that spans between these 3 atoms. There's other types of carbon-based structures that have delocalized bonding. And instead of having oxygen-carbon-oxygen connection, oxygen-carbon-nitrogen can also happen. Can also have delocalized bonding. So that same double-bonded oxygen to carbon with 2 lone pairs, but this time connected to a nitrogen. This nitrogen, it only has 2 bonds and 2 lone pairs, which is different. This is an anion. But these lone pairs, you can think about this lone pair moving from being a lone pair to being bonding, and one of those bonding pairs becomes a lone pair on oxygen. And you can draw a Lewis-Dot structure that has carbon with a single bond to oxygen, but this time 3 lone pairs, still bonded to H. This time we have a double bond between carbon and nitrogen and just 1 lone pair. So that's a resonance structure. Again, if you can do something like that, it means that there's a delocalized orbital that spans all of those atoms that those electrons can move between. You also can see it in a carbon-based molecule that's a cation. And here's a good example. Somehow a bond here was broken. There's probably another bond connected there at some point, but we formed this cation. Those bonding electrons were knocked away from some reaction. But here we have alternating double single bond. These bonding electrons can move over to here and we could form this structure. This is a different type of delocalized bonding that you haven't seen before, but it's still, the fact that you can draw two Lewis dot structures that are the same and go between the atoms, it implies that there's a bonding orbital that spans between all three of those atoms. So it has delocalized bonding. For this exam on this test, there won't be any questions about delocalized bonding, but if you're going on to organic chemistry, this is something that's expected that you know. And when you explain chemical reactions and chemical properties, delocalized bonding could be an important aspect to understand when it's explained to you. Carbon-based reactions, the reactions happen where the bonds are the weakest. And being able to predict bond strength is something you should be able to do, or at least understand, when the chemical properties are described for different functional groups. The strength of the bond is related to the bond length. That's a property you should be able to understand. We learned about it in Chemistry 162, and I'm pretty sure you should be able to fill in that blank for bond length if you're comparing atoms that are part of a bond as you go across the periodic table. You should also be able to say what happens to bond length when you compare atoms as you go down a family. Why don't you fill in these two blanks? Make sure you have the right answer, and then for each bond that's given below that, predict which one is the shorter bond. So is the CH bond shorter or is the OH bond shorter? Do the same thing down here for the FH bond compared to the bromine hydrogen bond. This next part, that looks like hybrid orbitals. We'll talk about that after we answer those questions above. So pause the video, unpause the video when you're ready to check your answer. As you go across a period, the atoms get smaller, which means the bonding orbitals that they form are relatively smaller. So we're comparing carbon versus oxygen, and both of them are connected to hydrogen. Oxygen is a smaller atom than carbon, so the oxygen-hydrogen bond would have the shorter bond length. As far as atoms going down the period, so we're comparing fluorine and bromine, and both of them are connected to hydrogen. Fluorine is a smaller atom. It would have a smaller bonding orbital that forms, so the FH bond has a shorter bond length. If you remember, this is the designation for what hybrid orbitals are formed prior to bonding. So there's sp3 type of hybrid orbitals that form, and sp orbitals that form. And we'll talk about this, refresh your memories, a little more on the next page. And then we'll come back and answer this question. So here's a list of hybrid orbitals that could form. And again, remember, you look at what's formed to predict what hybrid orbitals form prior to bonding. For carbon-based reactions, you only really need to worry about 4 groups for the most part. The hybrid orbitals that could form are sp, sp2, and sp3. You'll be using this terminology a lot in carbon-based chemistry, especially in the beginning. If I gave you 2 example molecules, you should be able to say if a hybrid orbital forms on an atom, and if it does, what type, and what 2 orbitals are used to make the bonding orbital. Now remember, the bonding orbitals, they could be sigma or they could be pi. So let me give you 2 molecules. One of them is formaldehyde, and you've actually answered that one a lot. You did it in the laboratory. And here's a carbon-based molecule. It's a methane-based, and there's a fluorine attached and a hydrogen attached to the carbons. If you remember, if there's only a single bond between the 2 atoms, it's always a sigma bond. If there's a double bond or a triple bond, there's always a sigma bond. If there's a second bond, then it's a pi. If there's a third bond, then there would be 2 pi bonds between the 2 atoms. There's always a sigma bond for all the examples we're looking at. So a question you should be able to answer: what's the 2 orbitals that are used to form the sigma carbon-fluorine bond, and what orbitals are used to form the sigma carbon-hydrogen bond? Why don't you go ahead and pause the video and see how well you remembered that. Unpause the video when you're ready to check your answer. For the carbon-fluorine sigma bond, the carbon having 4 groups would have sp3 hybridization. That hybrid orbital would overlap with the 2p orbital on fluorine. It's the 2p orbital that contains the single electron on fluorine. So these are the two orbitals that overlap to form the sigma bonding orbital. Again, the fluorine only forms a single bond, so there's no hybridization. As far as the sigma carbon-hydrogen bond, it's still sp3 hybridization for carbon, and there would be 4 of those sp3 hybrid orbitals that would form around carbon. For the carbon-hydrogen sigma bond, that sp3 hybrid orbital would overlap with the 1s orbital on hydrogen. Okay, for the formaldehyde example, why don't you do the pi carbon-oxygen bond and the sigma carbon-oxygen bond? 2 orbitals overlap to form a sigma bond, and 2 orbitals overlap to form a pi bonding orbital. Go ahead and pause the video and give an answer. Unpause the video when you're ready to check your answer. So remember, pi bonds are always formed from the overlap of p orbitals, and the p orbitals that have a single electron in carbon and oxygen are both 2p orbitals. The hybridization that happens on oxygen and carbon actually is the same type of hybridization, sp2 hybridization for both. The sp2 orbital on carbon overlaps with the sp2 orbital on oxygen to form the sigma bond between the two atoms. With that review of hybridization, I think we can talk about bond length with hybrid orbitals and understand it a little bit better. But bond length, we didn't learn this in 162, but bond length is different depending upon what type of hybrid orbitals are used to form that bonding orbital. It's no different than atomic orbitals being used to make a bonding orbital. The longer, the bigger the hybrid orbitals or atomic orbitals, the larger the bonding orbital that forms. And if you look at this hybrid orbital versus that one, and the quote here, well, the statement is S character. Well, this one, 50% of the hybrid orbital comes from the S shape, 50% from a P shape. One S and one P are used to make that hybrid orbital. Here, there's 3 p orbitals that are used and 1 s orbital that are used. So S character, this one, the sp, has larger S character. S orbital in the same energy level is more condensed than a p orbital. The p orbitals are a little bit longer. The more S character you have, the shorter the bond. So bond length decreases as the S character increases. sp has more S character. Okay, I didn't make up this definition, but that's what it's given, S character. So what if I gave you 2 molecules? What if I gave you methane and some alkyne molecule? And remember, alkyne means it has a carbon-carbon triple bond. The question is, which one has shorter bonds? And in particular, this only has CH bonds, so compare that CH bond to that CH bond. To do this, to answer this question, you need to know the S character. What's the hybrid orbital that's used to make that CH sigma bond? And what's the hybrid orbital here that's used to make that CH sigma bond? Go ahead and pause the video and write the hybrid orbitals that are used to make each one of those CH bonds, and then decide which bond is shorter, the CH in methane or the CH in that alkyne molecule. Unpause the video when you're ready to check your answer. So for methane, it's sp3 hybridization that occurs on the carbon prior to bonding. For the triple bond, it's sp hybridization. The alkyne, that CH bond in the alkyne, has shorter hybrid orbitals, which means the sigma bond between CH and this molecule is shorter. The bonding orbital that's formed is shorter because the hybrid orbital is shorter. In carbon-based molecules, there's a lot of bonds that contain hydrogen. And these bonds, some are stronger, some are weaker. Just like what we learned in acid-base chemistry a little while ago, you can look at bond strength, the bond that contains that hydrogen, by looking at the Ka value. And you should be able to fill in that blank. Once you pause that video and write larger or smaller, unpause the video when you're ready to check your answer. And if you remember, it's larger. More products are formed. This is a reaction. We saw HCl, that's an acid. Here's acetic acid. There's a Ka value. You could go to your information packet and find. Except, oh, here's ethanol. I thought ethanol wasn't an acid. Well, it's not considered a traditional acid, but that OH bond is relatively weak because of the high electronegativity nature of oxygen. Those bonding electrons are far away from H compared to the bonding electrons in a CH bond. It's relatively easy to break, and it can break if a water molecule collided, and there would be an equilibrium. Remember, the Ka just gives you an equilibrium. 10 to the negative 16th means it's mostly reactants, but you can form the anion by knocking that hydrogen nuclei away from the bonding electrons. And there's a Ka there. And even though if you added ethanol to water and used a pH meter, you wouldn't see a noticeable change in pH, it does occur. Oh, here's another one, and there's a Ka there, but there's no oxygen. Still, the CH bond that's in methane, so this is methane, it can be broken, and there can be a collision with a high enough energy that could knock the hydrogen away from its bonding electrons. So here we have CH, all CH bonds, that's a center atom's a C, which is really small. But that water can collide, knock a hydrogen away, and that hydrogen atom can bond to the lone pairs on water, and that lone pair can stay there, and we form an anion. So we have a lone pair there. The CH bond in methane is a lot stronger compared to the OH bond in ethanol, and that's why the Ka value is so much smaller. But there still is a measurable Ka value, and you wouldn't use a pH meter to get this equilibrium concentrations, but you could use some other sort of absorption using a spectrometer to get equilibrium concentrations. So even though these two Ka values weren't given to you, they are in tables if you went looking. In carbon-based chemistry and organic chemistry, it would be nice if they used Ka values because you're used to it, but they use pKa values instead. So pKa. Remember, pKa, it's a constant, and it's just the negative log of the Ka values. So instead of saying Ka values and saying how weak or strong a bond is, you can use pKa values. And if you plugged all these Ka values into here, we'd get a listing that would look like this. -7, 4.8, 16, and 50. And that's just plugging the Ka values into this equation. We said this, acids with a larger Ka value are stronger compared to ones with smaller Ka values. Or you could say acids are stronger when the pKa values get smaller. So as pKa decreases, acid strength increases. And this also says something about bond strength, the bond that contains the hydrogen that's breaking away. Bond strength, well, you should be able to fill in that blank. So, and bond strength either increases or decreases. Pause the video, unpause when you're ready to check your answer. Remember, acid strength, a stronger acid has a weaker bond. As pKa decreases, the strength of that bond is getting weaker. What if I gave you a chemical reaction and it's balanced, and I gave you pKa values of the two acids? You should be able to predict whether it's mostly reactants or mostly products. So here's the chemical reaction. You see some structures you're probably not that familiar with and some that you are. So here's a neutral carbon-based molecule, so there's that alkyne structure again. Here's ammonia, you've seen that before. You're given the pKa's. If we go from left to right, this bond is breaking, so here's the pKa value, it's 25. Ammonia, it has an NH bond. One of those NH bonds are breaking, and we're forming the anion form. But for this problem, you're given the pKa of that particular molecule. So pKa of 25, pKa of 38. You should be able to say if it's mostly products or mostly reactants at equilibrium. Go ahead and pause the video. Unpause the video when you're ready to check your answer. The side that has the stronger components, the other side will be mostly the other side at equilibrium. As pKa decreases, the strength of the acid increases. The stronger acid is on the reactant side, so it's mostly products at equilibrium. In organic chemistry, just like we did in our acid-base chemistry chapter previously, you can predict the strength of the bond that contains the hydrogen atom. So predicting acid strength. The first two, although the names may not seem like we've done it before, we've done those before. The first one is the element effect, which means what's the atom bonded to the hydrogen. And here are three different bonds, and you should be able to predict the strength of the bond by looking at the atom that's bonded to it. So here are three bonds, CH bond, OH bond, and an HF bond. So all of them contain the hydrogen atom. You should be able to predict which one would have the highest pKa value and which one would have the lowest pKa value. I'm going to give you three pKa values. One of them is 16, another one is 50, and the other one is 3.2. So when we're comparing the atoms that are bonded to H, C, O, and F, they're all either in the same period or the same family, and based upon either being in the same family or the same period, you use size or electronegativity. Why don't you pause the video and write the pKa values below those bonds and think about how you made that decision. Unpause the video when you're ready to check your answer. If the atoms are all in the same period, then you use electronegativity. Electronegativity changes more dramatically as you go across the period than the size change. As the electronegativity increases, the bonding electrons are further away from the hydrogen. So the weakest bond of these three would be the HF bond, meaning it would have the smallest pKa value. So this would be 3.2. The atom with the smallest electronegativity is carbon. So this is the strongest bond of the three, meaning it would have the highest pKa value of 50. And the OH would be in between, 16. If we were comparing atoms that are in the same family, like HF compared to HI, and I know you know this, HF has a pKa of 3.2. HI, its pKa value is either smaller than 3.2 or greater than 3.2. Why don't you pause the video and just mentally tell yourself the answer and think about what variable you're looking at that's giving you an idea of bond strength. So does HF have a stronger bond or does HI have a stronger bond? Unpause the video when you're done thinking. The pKa value for HI equals -10. It's a weaker bond than the HF bond. It's a stronger acid. When you're comparing atoms that are connected to H and the atoms are in the same family, as the size increases as you go down a family, the bond is weaker. The bond is longer, the average position is further away from the hydrogen, and it becomes a weaker bond. And remember, electronegativity changes as you go down a family, and electronegativity actually decreases, and that effect makes it a stronger bond. but the size of the atom changes more dramatically as you go down a family than electronegativity. The next factor that could affect acid strength is inductive effects. And I'm sure we didn't use that word in our Chemistry 162 series. We use something slightly different vocabulary, but this is electronegativity effects and neighboring highly electronegative atoms, neighboring atoms that are next to the bond that contains H. So if I gave two examples, like ethanol and this freon type of molecule, so there's 3 fluorine atoms instead of 3 hydrogens. We're looking at the OH bond, and one of them it's stronger and one of them it's weaker. One of them, the pKa is 12.4, and the other one it's 16. Neighboring suns can have an effect on neighboring bonds. Why don't you pause the video and decide which one's 12.4 and which one's 16? Which one has a stronger bond and which one has a weaker bond? Go ahead and answer it for one of them, because that would answer the other one. So pause the video, unpause the video when you're ready to check your answer. Having these neighboring supersuns has an effect on the bonding electrons, that OH bond. Those fluorines pull those bonding electrons a little bit further away from the hydrogen, and it makes the pKa value lower, meaning that OH bond is weaker. So this one is our stronger acid. Resonance effects, and this is something you're going to learn more in organic chemistry, but if you can have a bond broken and it can form a resonance structure versus not being able to form a resonance structure, the one that can form a resonance structure is more stable. It would have a higher pKa value. So two examples, it's ones we've seen before, ethanol and acetic acid. Both of them have the OH bond, and that OH bond on both can break, and the bonding electrons can stay with the oxygen, and we can form two different structures. So here are the two products that could form if both of them behaved as an acid. The one that can form a resonance structure is more stable, and that particular molecule that's forming that resonance structure would have a lower pKa value. And we already know the answer from other explanations. I mean, you could use inductive effects for acetic acid too with that neighboring oxygen. But the fact that acetate can form a resonance structure and this ethanol anion cannot means that this acetic acid, that's another variable that goes towards pKa values. The pKa value of acetic acid is lower than for ethanol. So what I wrote there, if the conjugate base, the acetate that forms, so if the conjugate base that forms can form a resonance structure, its acid has a lower pKa value. The acid has a weaker bond. Resonance structures are relatively stable structures compared to not having a resonance structure. Note, on the upcoming exam, I'm not going to ask any questions about factors affecting acid strength. But if you are going into organic chemistry, this is a topic you should be well versed in before you start that class. The last one is hybridization effects, and this one's a little bit harder to understand, but acidity increases as percent S character increases. This one's a little bit harder to think about, and luckily there's not going to be a question on the exam that discusses it, but it's the S character of the conjugate base that we need to think about when we're looking at pKa values of the acid. So it's the A negative that forms. So the S character, we mentioned earlier, S character and bonding orbitals. Well, those orbitals around an atom, they could just contain the lone pairs. So remember, when you have an acid like X and there's an H connected, when it reacts, it forms, the H goes away and you have the lone pairs that are there. Those lone pairs are in an orbital. As the S character of those lone pairs that are in that orbital, as it decreases, it means the acid it formed from is actually stronger. The pKa increases. S character, percent S character, is related to how big or how small the orbital is, whether it's bonding or a lone pair orbital. As S character increases, the orbital becomes smaller. It means those bonding electrons are closer to X, meaning whether they're lone pair here or if they're bonding, as the S character decreases, these bonding electrons are closer to X, further away from hydrogen. So as percent S character increases, acidity increases, pKa decreases for the acid that forms the conjugate base. This material, this hybridization affects the factors affecting acid. These first two ones are pretty easy to understand. Resonant effects is probably somewhat easy. Hybridization takes some thinking and some more rethinking, but it's definitely going to be chapter 1 when you get into organic chemistry. For this exam, for this class, use your practice problems to know what the questions are going to be like, but you won't see any questions asking about factors affecting acid strength. Being able to do some nomenclature and recognizing functional groups and drawing some structures, that'll be the majority of your test questions from this particular chapter.